Welcome to today's Explainer. Today, we are looking right under the hood of large language models. We're going to demystify the exact mechanisms of how they learn and unpack the foundational architecture that's driving all these revolutionary advancements in artificial intelligence. And the best part? You won't even need a PhD in machine learning to get it.
Okay, let's dive right into this massive paradigm shift. For years, the old natural language processing paradigm was honestly incredibly tedious. If you wanted an AI to translate French, you had to build a highly specialized translation tool completely from scratch. Wanted it to classify positive and negative movie reviews? Well, you had to build a totally separate sentiment analysis tool, again, from scratch, relying on massive amounts of human-labeled data. It was slow and the models were incredibly narrow. But now we've completely moved to a new paradigm. Instead of building tiny specialized tools, we pour a massive, universal foundation that can do almost anything. We train one giant model on oceans of text, and then just adapt it to whatever we need.
So we're going to follow the chronological journey of an AI mind today. We'll start with the NLP Paradigm Shift, move into the magic of pre-training, explain self-supervised learning, compare encoders versus decoders, and wrap up with fine-tuning and prompting.
All right, Section 1, the NLP Paradigm Shift.
This quote really hits the nail on the head. This shift away from training specialized systems from scratch unlocked a profound, literal game-changer of an insight. An AI can acquire knowledge of the entire world and human language simply by doing large-scale language modeling tasks. By exposing a neural network to vast amounts of text, it wasn't just learning words anymore. It was actually learning logic, facts, and reasoning. It was building a universal foundation.
Let's move to Section 2, the magic of pre-training.
Historically, teaching AI was a real struggle. Unsupervised learning minimized reconstruction errors, which was a good start, but it lacked direction. Supervised pre-training offered much better task transfer, but it was completely bottlenecked by us, humans having to manually create massive labeled data sets. The revolutionary leap forward here is self-supervised learning. This is where the model actually trains itself using raw text, requiring absolutely zero human labeling.
Which leads us perfectly into Section 3, Self-Supervised Learning Explained.
Now this is where it gets really cool, because the AI acts as its own teacher. Imagine taking a textbook, covering up a few words with your hand and guessing what's underneath, based on the surrounding context. That is exactly what self-supervised learning is. The AI generates its own supervision signals directly from raw, unlabeled text. It hides parts of the data from itself, makes a prediction, and then just checks the hidden part to see if it was right. By repeating this process billions of times across essentially the entire internet's worth of text, the neural network builds a profoundly deep understanding of how our world works.
So how does it play these guessing games? Let's look at Section 4, Encoders versus Decoders.
To easily grasp the heavy mathematical data happening here, you can just think of the training process as two distinct childhood games. Decoders play guess the next word. They read strictly left to right using auto-regressive modeling to predict the future. This is what powers models like GPT. Encoders, on the other hand, play fill in the blank. They get to utilize both the left and the right context simultaneously to figure out a missing piece right in the middle of a sentence.
And this brilliantly illustrates that encoder game, which is called masked language modeling. Take a look at the sentence. The masked bird catches the masked. Models like BERT use the surrounding context clues to calculate the absolute highest probability for what goes in those brackets. The model analyzes words like catches and bird and calculates that early and warm are the logical fit. By doing this over and over, the AI learns the deep, bidirectional relationships between concepts. It's not just blindly predicting forward, it's understanding the entire context simultaneously.
But researchers realized there was a slight flaw with using those artificial mask tokens. I mean, humans don't actually speak with the word mask randomly inserted into our sentences, right? It created this artificial discrepancy between how the AI trained and how it would actually be used in the real world. So they invented permuted language modeling. Instead of using fake placeholder tokens, the original text stays exactly the same, but the AI is forced to predict the words in a completely random, permuted order. For example, instead of predicting words 1, 2, 3, 4, 5 in a sequence, it might be asked to predict word 3, using words 1, 2, 5, and 4 as clues. This forces the model to capture far richer, broader dependencies without relying on fake placeholders.
We also reinforce this foundation by playing a logical matching game called next sentence prediction. We want the AI to understand complex relationships across entirely different sentences, not just within a single phrase. So we feed the model two sentences. Sentence A, it is raining. Sentence B, I need an umbrella. The model then has to classify, does sentence B logically follow sentence A? By playing this game, the AI learns narrative flow, cause and effect, and the broader coherence of human thought.
Once that foundation is fully poured, it's time for Section 5, fine-tuning and prompting, the on-the-job training.
Let's go right back to our construction analogy for a second. Fine-tuning is exactly like building a specific house on top of our concrete foundation. Our AI already knows English, it knows logic, it knows facts. Now we just slightly adjust its neural weights using a small dataset of labeled examples so it becomes a total expert at a specific job. Say we wanted to classify customer reviews as positive or negative. We don't have to teach it what the words terrible or amazing mean from scratch. We just show it a few examples of positive and negative reviews, and it efficiently adapts its pre-trained knowledge to this specific task.
But as these models got larger and larger, researchers noticed something absolutely incredible. Often, you don't even need to fine-tune them anymore. You can just utilize zero-shot prompting. When you ask a modern chatbot a question, you're interacting with a model that first had to contextualize billions of linguistic parameters by playing those fill-in-the-blank games. Also, it could eventually instantly adapt to a raw instruction. You just feed it input text, command it to identify the sentiment, and boom, it outputs the answer. Zero extra training required.
And what is truly mind-blowing about this modern architecture is in-context learning, which is also known as few-shot learning. By just embedding a few live demonstrations directly into your text prompt, you can teach the AI entirely new capabilities on the fly. We show it a negative example, we show it a positive example, and then we give it our real question. The AI recognizes the pattern within the context of your prompt and just solves the problem. You are effectively programming the AI using plain English without changing a single line of its underlying code or tweaking a single neural weight. It's wild.
It is honestly staggering how far we've come from the days of manually writing rules for grammar and syntax. So, I want to leave you with this provocative thought from our explainer today. If a simple childhood mechanism of guessing the next word gave us the incredible, world-aware foundation models we use today, what unimaginable scaling laws and capabilities await us in the future? When we give these AI minds even more data and ask them to predict the next million words, what new dimensions of logic and reasoning are they going to uncover? Thanks so much for joining me on this journey through the foundation of large language models. Keep wondering and keep learning.